Hello and welcome to another wonderful day of industrial chemistry. So today we are going to be talking about chemical processes or chemical processing. So this is the idea of taking a raw material and turning it into something. So in order to get to a final product, we often need to go through many steps of chemical processing, but we're going to be focusing on the individual components today. And one of the things I want to emphasize is that chemical processing doesn't always have to be something fancy. A great example is, as you can see, taking salt water, putting it in, or seawater, and putting it into a nice hole in the ground, and letting pan evaporation do the rest of your work so that you can extract mineral salts. So this is one of the most common ways you can end up with sea salt, is simply just letting evaporation do our work. Now, this is a great example that you can often use very simple techniques to do chemical processing, but the scale is going to be very different than we would typically do in a chemistry lab. But in order to understand what chemical processes we need to use, one of the places we should really start with is by looking at our raw materials. So most of our basic chemicals are going to be obtained from natural sources, which means we can subdivide them into three major categories. The first of which is going to be the atmosphere. So atmosphere tends not to have many fancy things like minerals, but is a good source of a lot of the industrial gases. So specifically nitrogen and oxygen, which constitute a good portion of the atmosphere, but also things like noble gases such as argon, which is a notable percentage of the atmosphere. But we also have things like the hydrosphere. So this is anything where water is involved, and it's going to be a ready source of a lot of our minerals. So pretty much most of your chlorides, but also a couple of other minerals. So as we saw previously, simple evaporation will get you a nice mix of these salts from which you can then try and isolate. But as things tend to be, we often focus on the lithosphere, which is going to be the planetary crust. So this is a good source of a lot of minerals, metals, and in the form of minerals such as bauxite, which contains aluminum, and hematite, which is a good source of iron. But there's also many more available. But it's also a good source of a lot of carbon precursors. So almost all of the petrochemicals you can derive. Usually we talk about oil, which is going to be our long chain carbons, but you also get short chain carbons in the form of natural gas. So this is things going from methane to butane. But coal, which is more or less solid carbon, is also a fairly good source for a lot of organic chemistry. But it is worth noting that sometimes we don't want simple carbon compounds. We need something a little bit more fancy, at which point the biosphere is often an additional good source. So this is going to give us a lot more complex organic materials. For example, this is how we first isolated cortisol, but it turns out that it's often hard to isolate these fancier compounds. So we often will make complex organic compounds out of simpler ones, which may be something as simple as fatty acids, for which things like soybeans and corn are a really good feedstock, or things like ethanol, for which we often use sugar, such as we can find in corn or sugarcane. So don't forget, a lot of organic compounds are often isolated from living organisms. But if I'm going to go beyond basic chemicals, we're going to often need to take these basic chemicals and then do some form of reactions or mixing in order to make a lot of our specialty or consumer chemical products. So let's go ahead and talk about how these products are going to be made. So one of the big things we should always remember is, like crude oil, most of our raw materials are not going to come pre-purified. They're going to become as a big mix of chemicals. And we'll talk about this a little bit more lately, but it's worth noting that, say, I want to go ahead and make plastics. So I want to take my crude oil and make ethylene, but I'm going to have a lot of compounds I'm not going to want. So while there is some ethylene in crude oil, there's also a lot of ethane, a lot of butane, a lot of long chain carbons, asphaltenes, gasoline, kerosene, plenty of things I don't want. So we often are going to be looking at how raw materials can be processed in a series of distinct steps, each of which has a single function. So I don't go straight from crude or oil to ethylene. I'm going to need to have a lot of individual steps. And that's what we're going to try and focus in on. And a chemical stream can essentially carry each of our reactants to products in between each of these steps. So the real art of industrial chemistry is going to be identifying what each of these steps are and trying to link them together to make an overall process. So we're going to take a lot of these steps and split them into two major categories. So the first of which are going to be chemical transformations of chemical inputs. So when I'm talking about a transformation, what I'm talking about is a reaction. So I have chemically transformed my reactant to something else. So in terms of our previous example, I may be trying to make ethene. Well, I might get that by starting with ethane and then removing two hydrogens. So this would be a chemical transformation. Any step that includes a chemical transformation, we call a unit process, as I'm going to process my chemicals. So I'm going to start using processing and operations a little bit differently. So if I'm a chemical engineer, or let's be honest, a chemist who works just on these reactions in an industrial setting, I'm going to be called a reaction engineer. So this is actually where my specialty lies, because I love myself some mechanisms. I used to always think if there isn't a chemical reaction, it isn't chemistry. Well, chemical engineers will definitely argue with that, because it turns out that reaction engineers are often the least well paid of in chemical industry. Where most of the pay actually ends up going to is going to be into the second type. But unit processes are essentially every type of chemical reaction you've seen. If there's a reaction, it's a unit process. The biggest difference is going to be about scale. So we often end up making materials at, say, maybe the 100-gram level at the very most in most chemistry labs. In industry, we pretty much start at about 10 kilograms, which means the reactors tend to be a lot bigger because they're going to be continuously processing and they're going to be continuously removing product, either if you have a flow reactor, like you see here on the left, or a batch or semi-batch reactor, which you see on the right, where product is coming out the bottom. And so we're going to have a lot of restrictions placed on these reactions because of the size and scale. One of the most notable, which is a lot of favorable reactions, are exothermic. But it turns out that if I have a reaction that's producing too much heat, well, that can quickly get away from me and cause things to blow up. So we're going to have a lot of restrictions on what unit processes we can perform. However, turns out that not all chemical engineering is unit processes. Most of it actually is going to be in terms of physical transformations. So this is essentially any step at which I have no chemical reactions occurring. So this is where I can change, say, my chemical feed, but no reactions. So this is going to include, these are going to be called unit operations. So I have a process if a reaction takes place. I have an operation if I'm just, say, purifying my material or mixing material. So again, some of our big classes of unit operations are going to be things like size reduction. So what we see here on the left is a ball mill. So this is where I put in a whole bunch of of metal ore, and I run it through essentially a big cylinder that contains a whole bunch of ball bearings. So I have a huge case of size reduction. But this may also include things like size aggregation if I'm trying to grow crystals, such as in our earlier salt example. But you also have one of the most popular ones, which is heating and cooling. because it turns out temperature control is a very big deal in chemical industry. So what you see here on the right is essentially a heat exchanger. And then finally, we have what we as chemists tend to think about the most, mixing and separations. So if I'm going to be a chemical engineer who works on these steps, I'm going to be called a process engineer. Now, what's important to note about most process engineers instead of reaction engineers is they tend to focus not just on these individual unit operations, but they're also more focused on how I link these unit operations together. And in fact, if you want to make money, process engineers typically make about 10 grand more than reaction engineers. So as chemists, yes, we may have chose poorly, but one of the reasons why process engineers make money is because you actually need a chemical engineer, and it's much harder to retrain a chemist to become a process engineer. So when I'm looking at processes, turns out one of the most important of these classes is actually going to be this last one. It's separations. So this is going to be our bread and butter of unit operations. And one of the reasons why is because we started with almost all raw materials contain a lot of unneeded components. And even if I have a chemical reaction, I'm going to often produce side products that, again, I don't want. So let's take a look at a good, relatively simple chemical industry example. So let's say I have a whole bunch of corn, and then I want to make bourbon. So I don't do this simply by just throwing corn into a fermenter. What I first need to do is I first need to go ahead and break the corn up. So I have to do size reduction. And then I'm going to need to filter out pretty much everything I don't want. So that's going to be the cob, the husk, all of the shells of the corn. I'm going to need to pretty much filter out everything except for the ooey gooey sugary inside of those kernels. And only then am I going to actually have a chemical reaction. Yeast take care of this, so this is actually the easiest step, is the actual reaction. A lot of the work goes into the unit processes, unit operations on either side, because once I even have my nice alcohol in here, all I did is I made beer, not bourbon. So I need to do a second batch of filtration because I need to get rid of all that wonderful yeast and mash and nice particulates because nobody wants gritty alcohol. And then we have distillation. So what I end up having is, in order to go from corn to bourbon in the simplest sense, ignoring any sort of mixing and aging, I still have 5 steps. And only one of them is a process. The other 4 are going to be unit operations. And so a lot of the effort is going to be put on these. And you may notice that 3 of them are essentially separation techniques. And even you can argue for size reduction. And again, what this really helps illustrate is that most chemical processes, most of my real work is actually going to be in separating out the components. So for example, it's going to be these filtrations, which is hard, and distillation, which is very tricky. Because if you get the distillation wrong, well, that's how you get moonshine that turns you blind. And it turns out that separations are perhaps one of the biggest factors in the cost of chemicals. So we see here on the right is a great example of how much the difficulty of separations really drives cost. Because what you see here on the right is if I have a certain chemical that is contained in a natural source, be it citric acid in fruits, luciferase in fireflies, insulin in animals, what you see here is in the substrate for which I generate the material, how prevalent it is, and on the right you see cost. It turns out there's roughly a straight line going in between factoring these. So simply put, the more difficult it is to isolate the chemical we care about, the more it's going to cost. Some are going to cost a little bit more, like insulin, because of things like the high demand. Some things a little bit less, like copper, because there's some nice tricks you can pull to remove copper. But in general, it's worth noting that in chemical industry, separations account for the majority of all of the chemical plant cost. It isn't running the reactor, it's doing the separations. So what this really does help show is that you can generally predict the cost of a product just by knowing how prevalent it is in the product stream of your chemical reactor. Now, one of the reasons why this tends to be the case is because most chemical separations can be very energy intensive. And we'll see that as we walk through some systems. But they often end up being very intensive in energy or in resources. So let's go ahead and work through some example separations. So let's say I've got an industrial plant. One of the first things you should think about is in what mode your chemical is moving around in. So, am I moving my species around as a solid, a liquid, or as a gas? This is going to vastly change the cost of the plant involved, as well as the separation techniques I can use. So what we can do is, no matter what system I'm using, I can divide most of my separations into 4 major categories. So the first of which, and this is one we use a lot in chemistry, is the addition of a second substance. So I can add a second substance to my starting material to help extract out what I care about. So one of the great examples is, who doesn't love this one in organic chemistry? Solvent extraction. So this is where I add a second liquid. So a good example of this is going to be, say, I have a nonpolar substance in water. I add a little bit of an alcohol. I can go ahead and pull out my organics. Or let's say I've made a fermented sample of penicillin. Turns out you actually extract it by adding ketones. And then once you have the ketones, you can isolate all your penicillin from your ketones much more easily. So one of the strengths of this one is that it's actually fairly easy and fairly easy to scale up. But it also has a major weaknesses in that, guess what? You added another chemical you need. You added the second solvent, whether it's an extra polar solvent or an extra non-polar solvent. And it turns out that maybe those ketones don't come cheap. In addition, the other major weakness we have here is going to be the fact that, oops, all I did was change the system I need to extract from. So now I need to extract penicillin from a ketone instead of water. Now this can be a lot easier, but it still means we have extra steps. We also have things such as drying pools, where we have, as we see here on the right. And so if I'm dealing with a drying pool, then guess what? I added air. And this is one we don't often think about. But that's more or less what a lot of evaporation techniques are, is going to be adding air to allow water to evaporate. So now I'm not removing the species I care about, but I'm actually removing the solvent. So these ones are nice and cheap because guess what? Air is a cheap material. But as you see here, they often need to be quite large in order to extract a sufficient amount of your solvent. Now there's some ways we can improve this, but in general, this is a fairly big weakness. But if you're dealing with cheap substances like sea salt, it's not a bad option. We can essentially accelerate this idea of drying pools by gas stripping, which is more or less going to be aggressively pumping air into a system. So what you see here on the right is essentially a gas stripper. So let's say that I'm working with wastewater, and I want to go ahead and pump out, well, vault of organic carbons, which are often toxic, and ammonia and hydrogen sulfide out of my wastewater treatment plant because these are all environmental contaminants. Well, one of the ways you can do that is literally by pumping air through the system, and all of the contaminants end up in the all end up in the air that we pumped in. So gas stripping is actually, again, a pretty nice technique, but it does require that our subs, so it's fairly cheap because all we really need is a good pump, but it does have a weaknesses because I'm still going to need to separate out these components from the air. In addition, it does require that we have a volatile gas to remove the species. So again, one of the problems with a lot of these techniques is that they often have a fairly low yield of in terms of rate of how fast I'm removing the species I care about, whether it's my solute, whether it's my solvent, or whether it's a volatile species. So one of the techniques you can use to speed up these processes is by adding in heat. But we also have the other option of removal of heat. So the classic example of um, of using heat for separation is distillation, which is more or less the idea of I take a starting material, I heat it up, and then I separate out all of the components based on boiling point. So this is a great technique because the only major input I need is going to be heat. I don't need to add in any other chemicals, which means I don't have to buy anything. But unfortunately, this requires a lot of energy. But in the current energy climate, this is still one of the cheapest separation techniques. So it accounts for the vast majority of real world separations. The only major weakness is that it's quite energy intensive. Thus, one of the reasons why, despite being a cheaper technique, separations is still one of the most expensive parts about chemical processing. We essentially also have the slower version of this, which is evaporation, where I'm just removing, say, a solvent. So you can think about things like rotovat, where I'm going to you can use this to either recover the volatile component, such as recovery of ethene from alcohol, or you can use it to recover the more recalcitrant component, such as if I'm trying, such as trying to simply remove, say, hexane from water. So again, this one can be a little bit slower, but it's still fairly good for species where I have a good portion of both of the compounds of interest. Similar, we also have crystallization, which is often done instead by cooling. So if I cool my product down, I can start to see solid crystal formation. So this is a great option and is a classic favorite in industrial separations. However, one of the biggest weaknesses of crystallization is that we often end up producing impure crystals. So there can be a rather large portion of contamination in our end product. Now, these are actually some of the most, the addition of a second component, such as solvent extractions, and the additional removal of heat are the classic favorites of industrial chemistry. And they tend to disfavor the only thing we ever talk about in most chemical labs, which is the use of physical barriers. So this is what we often talk about, is the idea of pushing my chemical system through a physical barrier, solid substance. So the classic example of this is filtration. So a great example of this, as you can see on the right, is separating out hydrogen gas from a gas mixture by essentially using a fine filter, so only hydrogen can move through. So this is actually a nice, simple process, and it's really good when we have different sizes of compounds. However, there is a major weakness to this system that prevents it from being used, which is the fact that most filters don't last forever. So you often need to either take the time to be able to clean out your filters, and time is money, or you need to regularly replace filters, which is again another major weakness of trying to use filtration at large scales. Then we have things like chromatography, which anyone who's in or has taken biochem will know is a classic favorite of biochemistry. So, for example, if I'm trying to isolate human growth hormone, chromatography is wonderful because it is great at separating out things that are very vulnerable to destruction by heat and can be very fragile to the use of other chemicals. So this is its biggest strength. The weakness is anybody who has done chromatography knows that this is a time-intensive process. You often are going to need to constantly change out your chromatography columns. It is slow and expensive, and you only ever use it as a last resort. And a last technique that is kind of dear to my heart is the idea of adsorption, not absorption, adsorption. So this is the idea um, of adhering a gas or sometimes a liquid to a solid surface. So a great example of this is, say, using amines to remove CO2 from a coal plant. So if I've got a nice coal plant, I'll run it through, I'll first cool down my gas, and then I'll run it past the carbon capture facility, which is essentially a big tower full of amines, which CO2 adsorb to the surface and then are isolated. So this is a nice kind of simple technique. It's really good for compounds like CO2 that are a minority component of a product, because despite what you think, CO2 is a minority component of most flue gas because most of it is N2. But the biggest weakness is I need to be able to remove the CO2 back off of the amines. And this is actually true in most adsorption cases. So I still often need to spend a great deal of heat to desorb any of my bound species, which is one of the major reasons why we still don't have cheap carbon capture techniques, is because of this weakness of the energy requirement. But sometimes you're actually really lucky and you can use this fourth technique, which is the use of external fields. And this is fantastic because one of the things you can do is be very lucky and use an external field such as gravity or density to separate species based on things like weight. So a great example of this is centrifugation. So this is a nice, simple technique. It's still relatively cheap, but unfortunately it does require a very significant density or weight differences of the species I care about, and can still be quite energy intensive. For example, you can usually tell when somebody is trying to enrich uranium because of the large spike of energy use from the centrifuges involved. Other things you can do is try and separate based on an external field, such as electricity, for things like electrolysis, where you're separating things based on charge. So again, electrolysis, it tends to be a fairly effective technique at separating based on charge, but is very rarely used because of the fact that it has a large energy input and it can be very slow. But there are some things where there is no other good option. A great example is electrolysis is pretty much the only way to isolate pure aluminum because it is fairly light, it mixes well with the impurities, and well, it's too reactive for most chemistry to kick in. So you need to essentially separate it based on charge, and electrochem saves the day yet again. And again, sometimes you're very lucky because it may have a magnetic charge or a magnetic field, at which you can use magnetic separation. So this is typically used for a lot of iron-containing compounds because we don't have too many ferromagnetic materials. So it's very limited in use, but if you have ferromagnetic materials, go for this one. However, what I've done is I essentially listed off a whole series of unit operations. However, it turns out the real art of industrial chemistry is pretty much being able to combine these unit operations and our processes, because there's usually a reaction hiding in there somewhere, in a balanced way. So this means we're going to have to learn how you can select the correct unit processes and operations. And then you need to carefully link these together such that you don't end up generating leaks in terms of losing product, have too much buildup where you have too much coming in and not coming in enough coming out, or the reverse of dry units. And it's going to be this idea of linking together processes and operations that we're going to spend most of the rest of the semester focusing on. Because this is where, as chemists, we tend to have the largest weak spot. And hopefully, this course will help shore up some of these weaknesses. So, next time, we're going to be talking a little bit more about how we can generate abrasive framework to combine these unit processes and operations in a nice, convenient way. Till then, take care.